Okay, good afternoon. All right, everyone looks thirsty for knowledge. So I'm glad that I'm talking, not listening at this point in the day. It's kind of hard to listen. What time did you guys start? 9. I commend your diligence. Good. So let's just do a quick recap of the stretch discussion. As I mentioned, one of the last things we had talked about was this dimensionless stretch sensitivity. And so I made that plot of the flame speed as a function of kappa. We said that this slope, embedded in this slope, which is this derivative, embedded in this slope is all the physics of non-unity Lewis numbers and differential diffusions and Serre effects and Dufour effects and gas expansion. It's all buried in there. And so a lot of the more of the phenomenological stuff that I talked about earlier, we can actually, you can make plots like this using, modern tools like the post-flow premixed flames that is standard package in Chemkin, or in some of the other in Cantera, or some of the other canned chemistry solvers. And so a lot of some of the more phenomenological expressions that are out there, there are expressions for Markstein numbers or stretch sensitivities as a function of Lewis number and gas expansion, which are based upon one-step kinetics, and those are a very useful approximation and first step towards understanding things. But I think a message for those of you is that a lot of this stuff is very useful for research, for scaling data, and for understanding experimental tendencies. And so there's no reason to use phenomenological expressions or expressions derived from detailed kinetics when you can just go in and use calculations. And we do it routinely in our lab, and I know other people routinely do it as well. It's a really, really nice tool. You can eliminate a lot of phenomenology. As a simple example, blow-off. I've talked about this connection between blow-off and stretched flames. We'll talk about this in a little bit later. But there's this thing that we call the extinction stretch rate. There's a maximum. We've talked here about weak stretch. What we're going to talk about next is strong stretch. As you start to further and further stretch a flame, at some point it extinguishes. And it turns out that you can oftentimes very, very nicely scale blow-off limits by scaling a fluid mechanic time scale, like a characteristic velocity scale and a length scale, with a calculated extinction stretch rate. So for example, if you measure a blow-off condition at one condition, you can oftentimes figure out where blow-off will occur with maybe a change in fuel composition or a change in preheat temperature of the air by simply doing a detailed kinetic calculation and figuring out how the extinction stretch rate will move with composition. And so there's a lot of correlations out there, just pure brute force correlations for blow-off, and we don't need them anymore. They were great. They served a wonderful purpose. I don't know if any of you have Lefebvre's gas turbine combustion book. Does anyone have that book? So there's lots of correlations in there for blow-off. They were great. We don't need them anymore. We have much better understanding of what's happening, and we have these really nice tools. Okay, so as I mentioned, all of this weak stretch physics is buried in this Markstein number. One other thing that I had pointed out and talked about earlier, and let me just come back to it, is this thermal diffusive instability. I had talked about how so the stretch effect is a mechanism of instability in flames. And we're going to use the word instability a lot, particularly tomorrow when I talk about thermoacoustic instabilities and hydrodynamic instability. Again, what I'm talking about here is just a flamelet by itself having a spontaneous tendency to develop wrinkles. And we talked about how the Darius-Landau instability, which is a gas expansion-induced instability, the thermal diffusive instability is an instability due to the stretch sensitivity of the flame. And so it turns out that when you do the analysis, if the Markstein number is less than 0, flames will be thermodiffusively unstable. And the reason for that is, as you can see here, that this flame right here is positively stretched. And so, if the flame speed, we'd said SU on, well, I don't need to write this down. I have it on this page. Well, never mind. It's we wrote that expression earlier. So if the flame is is positively stretched, so if kappa is positive, that means that the flame speed will increase at these points if the Markstein number is negative. And so if the Markstein number is negative, this point in the flame will have a higher burning velocity. Similarly, this point on the flame will have a negative stretch rate, and if the Markstein number is negative, then this point will have a lower burning velocity. So bottom line, Markstein number less than 0 are unstable due to the thermodiffusive instability mechanism. And conversely, if the Markstein number is greater than 0, it's thermodiffusively stable. And in fact, people have worked out dispersion relationships which more generally include both the Darius-Landau instability and the thermal diffusive instability, because both of them are acting at the same time. And usually what happens is that long wavelength disturbances are unstable due to the Darius-Landau instability, but the thermal diffusive effect becomes stable, at least for Markstein number positive flames. What you'll generally find is that they're still unstable to long wavelengths because of the Darius-Landau instability, but very short length scale disturbances are stabilized by the thermal diffusive instability. Whereas if a flame is thermodiffusively unstable, then a much broader range of length scales is unstable. And that's actually responsible for, oftentimes when you look at, for example, lean hydrogen flames, I think I showed you some images of those earlier. These are fairly classic type pictures of lean hydrogen flames where you have just the spontaneous formation of these cells, and this is due to the thermal diffusive instability. Okay. Well, I want to talk now about, still talking about premixed flames, stretch premixed flames. I want to talk about strong stretch effects. All right. So what we did before was that whole definition of Markstein number. It's derived from linearizing around 0 stretch values. So it's intrinsically a weak stretch concept. So what happens when we have strong stretch? And there's really 2 major points that I want to emphasize for you that show up. One is that you get we have to start differentiating between displacement speeds and consumption speeds. So I've referred to that before. Now I'm going to hit it head on. The other is that you get extinction phenomenon. And so I'll talk about both of those. All right. So let's come over here and let's read what I've typed up here. So the displacement speed, we're going to define that as the speed at which, and this is the flame, that's really not precise, the speed at which some reference isosurface is moving with respect to the flow. So let me draw you a picture to illustrate this point, because let's assume these are isotherms, and I'm going to really blow up the flame, really make it thick. So this would be, if this is temperature, it looks like that. All right. Now I'm going to draw a couple different things here. Now here's my velocity. This is just a flat flame for now. Now we know because of gas expansion that the velocity is going to accelerate. And in fact, for a 1D flame, we know that rho times u is a constant, right? It's going to be a constant at each point. And so as the temperature increases, as the density drops, the flow is going to be accelerating. So when we talk about the flame speed, oftentimes what we're talking about is the velocity of the flow with respect to an isotherm right near a value near the unburned value. So I'll call that u, and I'll call this v. Okay? So oftentimes the flame speed is defined as the velocity with respect to that isotherm, the 300.1 K isotherm. And that, in fact, is the, you know, and for an unstretched flame, that's a good approximation for example, if you had a tube filled with non-reactant gases and you lit a spark at one end and you watched how fast that flame would move, for that flame would basically move at that unburned gas speed with respect to, it would move at what I've called SU with respect to the gases in front of it. All right? But there's no reason why that definition for flame speed is unique, right? I could just as well define the flame speed with respect to the 400K isotherm, or the 500K isotherm, or the 1200K isotherm, or the adiabatic flame, or the final flame temperature isotherm. And in fact, what we oftentimes would call, so the velocity of the flow with respect to this isotherm, we've called that SU. I've also called this SB, right? This would be the velocity of the flame with respect to the burn gas isotherm. Now, okay, so that's what I'm trying to say with this point. This value, this displacement speed, and I dropped it now, but you know, I'm going to give it a subscript D to denote that this is a displacement speed. That value, it depends on a reference surface. All right, so again, this is not a point which you'll find in most combustion textbooks out there. So those of us who kind of grew up learning about flame speeds, it's a little bit uncomfortable to learn how ambiguous a concept it really is. And the reason, and as I'm going on a little bit more, the reason fundamentally it's an ambiguous concept is because flames aren't sheets. Flames are distributed reaction zones. They're volumes, right? But we're trying to take all that volume, all the stuff that's happening in the volume, and collapse that to a sheet, which is a great simplification if all the length scales in the flow are much, much longer than the flame. If all the other gradients are large with respect to the flame thickness. As soon as we start getting to situations where velocity gradients start occurring on a scale that is on the order of the flame thickness, the very concept of a flame speed starts to become very ambiguous, very, very definition dependent. You can define something, but the number that you get, the answer that you get, is very, very definition dependent. In fact, as we'll talk about on this slide, you can, in fact, get negative displacement speeds. So how many of you are familiar with negative displacement speeds? Yeah, which the first time you learn about negative displacement speeds, the first time I was like, wow, those theoreticians who invented this need to go back to where they came from because they need to see real flames, because what's all that about? You know, I didn't think much of it. But the reality is the displacement speed, when it's negative, what that means is that the velocity is actually the bulk velocity. So I've got my picture here. Here's my isotherms. Here's reactants. Here's products. In fact, a negative displacement speed would be a situation where the bulk velocity, the convective velocity, is going from products to reactants. And this happens. All right. Now, I want to emphasize what we're going to talk about later, the consumption speed, the net, which is a normalized net consumption rate of reactants, which is a volumetric quantity. That's always going to be positive. But the displacement speed can be negative. And so I'm just and we'll talk about this a little bit more later, but I just bring this up to point out the ambiguity and even the fact that you can sometimes even get totally nonsensical results. And displacement speeds become negative when you have very highly stretched flames. And I'll give you two examples where displacement speeds happen. One of them shows up in geometry like this. If you take a stagnation geometry where you take premixed reactants and you stagnate them into products. Okay? What happens is that for low stretch rate, the flame sits somewhere around here. And it's a stretched flame because you get this, you know, as we talked about before, you get this divergence of the velocity. It's a positively stretched flame. As you increase the stretch rate, the flame gets moved closer and closer to the stagnation plane, right? And beyond some stretch rate, the flame will actually move across the stagnation plane. All right, so once the flame is on this side, the flow velocity is going that way. That's a negative displacement speed. So you might say, what's going on? Are products getting turned into reactants? Is entropy going down across the flame? What's happening? Does anybody have any ideas? Pardon? Yeah, I mean, basically what's happening is the flame is still getting fed reactants, but diffusive fluxes are so strong that the flame is getting fed reactants by diffusion. So you can see, you know, obviously there's going to be no reactants on this side of the flame, lots of reactants on this side of the flame, and you get these enormous gradients. And so you get very strong diffusive flux. So if you were to add up the net flux through the flame, if you were to add both the convective and the diffusive part, there would certainly be a net flux of reactants going in the right, quote, the correct direction through the flame. But if your definition of displacement speed is based upon a convective flux definition, i.e. bulk velocity, you can actually get a negative value. Okay? Well, this is something that shows up in the lab. A place where you can get negative displacement speeds in real flames, real turbulent flames, occurs when at tips of positively curved flames. So there's some nice work by Jackie Chen again, who I've referred to before, who has shown this. So reactants, products, these parts of the flame can actually have negative displacement speeds. And what's happening is the flow velocity is actually, the bulk velocity is actually going in that direction. Something like what I've drawn here. The bulk flow velocity, again, is going backwards. It's not that products are getting turned back into reactants and that entropy is going down. Rather, what's happening here is that you're getting just these super strong gradients and there's a net flux, a diffusive flux of reactants through the flame. So there is actual heat release and there is consumption of reactants, but the bulk velocity is actually going the other direction. Yes? Okay, so the question there was, is this related to the flame speed in a lab coordinate system versus a flame coordinate system? And the answer is no. The displacement speed is defined with respect to some isotherm. So that would be the displacement speed. Flame speeds, by the way, are always defined. Well, displacement speeds are always defined in a flame coordinate system. So on a coordinate system moving with a given isotherm, so in other words, if you have, let's suppose that you have an element of a flame, and at any given point, you have a velocity vector. I'll call that U unburned, which is a velocity vector. You have the flame. I'll just say that. VF is the flame element. And let's see if I can do some vector stuff on the fly. The displacement, the displacement speed will equal, and I'm probably going to be off by a negative sign or something like this, but VF dot N minus U unburned, the unburned displacement speed. And I'm already messing up my nomenclature, sorry. So the displacement speed is defined as, so VF is the velocity of the flame sheet. And so if you're riding along if you're moving with the flame sheet, the displacement speed is the velocity that you see with respect to if you're riding on a given isotherm. So the difference between displacement and consumption speed is not a coordinate system difference. Yeah.
We have a negative displacement speed in case of flame propagating upwards in a horizontal, sorry, in a vertical duct.
No, it would not be, because in a okay, so the question was, if I have a tube filled with gases, if the flame is propagating upward, would it be a negative displacement speed? The answer would be no, or it would not. It could be very positive, because again, the displacement speed is the velocity of the gases with respect to that isotherm. So there's or the, I guess with a dot.
So because you have products that are upstream, that are downstream of the flame, that might propagate upstream.
Yeah, so I think you're talking about a closed tube where the gases would, I still, what that would do is it would, that would give you, that would increase the flame velocity, but I don't think it would give you a negative displacement speed. What it would do is it would just shove the whole gas column upward, and so the velocity of the flame would not equal the flame speed in that situation. So, in other words, if so if I have a tube, if I have quiescent gases, so if this is reactants, this is products. If the gases are quiescent, the flame will be moving, Vf, and it will be moving with the displacement speed. All right. If the scenario you're talking about, if I cap it here, then what's going to be happening is this is going to be acting like a piston and driving the whole thing up. And Vf, if I remember correctly, it equals this. That it's bigger than the displacement speed because gas expansion causes a whole net motion of the thing upward.
But you won't have the products which are less dense than the reactant. So the product should move upwards. And is there a chance that it might go through the flame?
Yeah, and so this is backwards, I think is what you're telling me, right? And the answer to that would be no. You would not get a negative displacement speed purely from the fact that the product gases are moving. That's not what's giving you the negative displacement speed. That's a great question. Yes?
Can I say that reactants are diffusing faster than the ignition criteria across the flame? Why will the reactant cross the flame without even igniting?
The reactants are not crossing the flame without igniting.
So it is diffusing into the flame and then burning.
So, you're talking about this picture?
Yeah.
So in this picture, what you're asking is how are reactants getting to the flame? There's only one way, it's through diffusion. So the reactants are not crossing the flame without burning. Rather, it just goes to the issue here is the displacement speed is based upon the convective flux term only, right? Reality is you have both convective and diffusive fluxes, and in these strongly stretched configuration, the diffusive fluxes are enormous. So if you defined a displacement speed not just as a convective flux, if you defined it if you gave it a convective and a diffusive term, it wouldn't be negative. There's two ways in which mass is transported, right? One is through convection, the other is through diffusion, you know. But this definition of displacement speed only includes one of those terms, which is why it can go negative. Yes?
Just out of curiosity, if given those flow rates and for a cold case without the reaction happening, if we ignited at that point, what do you think might happen? When it's not ignited.
So if I started with this without a flame and I turned the flame on.
For the same flow rate.
Well, let's see. Well, I would imagine if I turned the igniter on right here, my guess is you'd probably see the flame move backward. That'd be my guess. Okay, let me keep moving here. Okay, so that's the displacement speed. So the consumption speed, what this is so again, let me just summarize. Displacement speed is the velocity defined with respect to a reference surface. Always defined with respect to a reference surface. All right, so you have to be clear about what that reference surface is. A consumption speed doesn't have that same ambiguity, because what it is it's a volumetric integral of either the heat release rate or a species consumption rate, and then suitably normalized to give you a speed. But really what a consumption speed is it's a consumption rate per unit volume or a heat release rate per unit volume. So the way that it's typically defined is by integrating along a streamline. You can either take the energy equation and integrate it along a streamline and then normalize it. So in other words, I can't read that, and I bet you can't either. Here's the energy equation, here's your convective term, your heat release term, and your heat flux and your enthalpy flux due to heat conduction, your enthalpy flux due to species conduction. And then, so you can take this thing and you basically integrate it from before the flame to after the flame, and I've called that the integral from minus infinity to infinity. Well, if you integrate from before the flame to after the flame, this term will go to 0, and you end up with just these two terms. This term right here is just the net rate of heat release from the flame. This term right here is simply just the product of the density times the velocity times the enthalpy of the reactants minus the density times the velocity times the enthalpy of the products. And what you can end up with then is a definition for the consumption speed defined either with respect to the reactants or with respect to the products. That's the U or the B. And I apologize, this text is so small. But let me just write it up here for those of you who are in the back. So for example, what this is saying is that SU consumption will equal the integral or the net heat release from the flame divided by the sensible enthalpy of the products minus the sensible enthalpy of the reactants. And depending upon which density you use, if you use the unreacted or the reacted density, that's going to give you either a consumption speed based upon the reactants or products. Now, this is a pretty typical definition for the consumption speed. You could also go to any species equation that you want. You could use the fuel, the species equation for the fuel, for some product, for some intermediate radical. And you could also do the same process, and you could define a consumption speed. So for example, from your species equation, you could define a consumption speed, and so W dot of I would be the reaction rate of species I. So the net, and again, the integral from minus infinity to infinity is the net production of that species normalized by its value in the products minus its value in the reactants. And then you have some reference density. The density is defined either with respect to the reactants or products. That's a consumption speed. And so these, as you can see, there's no reference surface that these are defined with respect to. They rather are, it's really a normalized volumetric reaction rate or a normalized heat release rate. So if you actually, and here I just show a couple calculations for you of what these look like. So this is the conditions at which this is a detailed kinetic calculation of a symmetric premixed flame. So I have premixed reactants stagnating into each other, so I get two premixed flames. And this would be a flame with a negative Markstein length, because it's a lean hydrogen CO flame. And I'm plotting here the calculated flame speed as a function of kappa. This is the displacement speed, all right? So, and the displacement speed is increasing with kappa. Here is a consumption speed from the energy equation. Here's a consumption speed based upon the hydrogen destruction rate. And you can see that they're different. So, and what you can also prove and sit down and prove that the consumption speed of an unstretched flame will equal the displacement speed of an unstretched flame, right? So this is why many of you may not be used to these concepts, is because it turns out that they're equivalent. that the speed of the reference velocity, the velocity of a reference isosurface is exactly equal to the normalized chemical production rate normalized by the density of that same isosurface. But as soon as you start stretching the flame, those aren't the same. And by the way, for those of you who work in turbulent combustion, there is similarly a difference in the turbulent flame speed is a similarly ambiguous quantity. And you can talk about a displacement turbulent flame speed, which is defined with respect to some progress variable isosurface, and a consumption-based turbulent flame speed. And again, they're not the same. And the reason they're not the same is fundamentally due to lateral diffusion or convection. Stuff is going out your sidewalls of your control volume. Okay. All right. Yes.
Is the displacement, negative displacement flame speed somehow related to blow off?
That's a great question. I would say not necessarily. My guess is that probably in a real flame, the flame would blow off before the displacement speed becomes negative. The phenomenon of blow-off, what causes blow-off? The blow-off happens when the flow is moving faster than the flame speed everywhere, right? And there's no reason that the displacement speed has to be negative for you to have that, for that to happen. That's really kind of basically a kinematic condition. So for a sufficiently high velocity, you could have a very, very strongly positive displacement speed. But if the flow velocity was high enough, you would never be able to have that kinematic condition where the two match at some point in the flow, and the flame would blow off. All right. Okay, so that's one point that I want to make about strongly stretched flames, is this difference between consumption and displacement speeds. The other thing that happens is that when you strongly stretch a flame is that for negative Markstein length flames, a little bit of stretch is a good thing for it, right? Well, a little bit of positive stretch is good for it. For a positive Markstein length flame, a little bit of negative stretch is good for it. But too much stretch disrupts the flame structure to such a point that at some point, for high activation energy flames, the flame just extinguishes. All right, and so these are calculations. I showed you these calculations before. These are displacement speeds plotted as a function of a normalized stretch rate, and you can see that these are negative Markstein length flames. It's a lean hydrogen CO flame, and so the flame speed is the displacement speed and the consumption speed are both rising as you stretch the flame. And then if we just follow this curve, you can see the curve, starts to get this nonlinear dependence. It reaches a peak. What's interesting about these high activation energy flames is it peaks, it drops, and you can just barely see. There's actually some stuff happening in there. If I were to zoom in on that region, what you would see is it reaches a peak, and then it comes down, becomes vertical, and then it extinguishes. And I think Professor Seshadri talked about this. This is dashed because it's a possible solution of the equations, but it's an unstable solution. So you would never see it in nature. But you can see how small a region that is. You probably can't even see it, that distance between there. But you can see that these values, these peak values, if I remember correctly, all these calculations were performed for a mixture with an unstretched flame speed of 34 centimeters per second. So you can see that stretch causes augmentation of the flame speed by about a factor of 3. So it's a very significant effect. But also, too much of it, you get extinction. And basically, And it's a very abrupt extinction. Yeah.
Such increases, there is a competition between the heat generation versus the heat loss because of chilling. That's where we see the turning.
Yeah, so you're saying what's causing this right here? So the lateral, I would, it probably is somewhat configuration dependent, but the lateral losses, enthalpy losses, at some point just become so significant, and these flames are so temperature sensitive that you go from a very vigorously burning state to zero burning with a very, very small change. That's what happens in high activation energy kinetics. When you have high activation energies, that just means you have very, very strong temperature sensitivities. So really minor temperature changes can have very significant effects in certain regions of the flow, of parameter space. But what happens is as you can see, is there is no solution. So if you have in fact, if I were to draw this curve would continue, it would come down to zero, and then it would loop back. And so what happens is you jump from the strongly burning solution, this doesn't go to zero, to a value of zero discontinuously. So if you're increasing stretch rate, you would see the burning velocity go up, 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 up. You'd see it drop just a little bit, and then all of a sudden, bang, it would go to zero discontinuously. And again, high activation energies is what makes that happen, is that when you have high activation energies, things don't vary smoothly and monotonically to zero. You have these S-curve type behaviors. Okay. And so I'll show you a couple data sets here. So this is that same data. Okay, this is that data where I've shown it in terms of the normalized stretch rate. This is that same data which I also showed you earlier. Now it's dimensional stretch rate. So just as I talked about, the dimensional sensitivity of the flame to stretch goes down as you go up in pressure because the flame's getting thinner. In the same way, as you go up in pressure, the dimensional extinction stretch rate goes up. All right? So flames, higher pressure flames are able to withstand higher fluid mechanics straining. And again, this is a flame thickness effect. And in the limit as the flame goes to zero, if flames really truly were infinitesimally thin, they would not be sensitive to stretch because stretch is fundamentally a finite flame thickness effect. It's that lateral diffusion or lateral convection effect. But this is an interesting one, and you know, for those of you who are doing experimental work, curves like this make me nervous because what it shows is that usually in the lab we like to run things at 1 atmosphere, but many applications are running at very high pressures. And so suppose you're trying to understand blow-off, for instance. And I've argued that blow-off is related to extinction, that the flame simply can't hang on in these very high stretch, high shear regions, and it locally extinguishes, and then the flame basically blows off. But what you can see is that, okay, if you're doing a blow-off experiment at 1 atmosphere, but you're trying to understand what's happening at 15 atmospheres, the value of stretch that the flame can withstand is well, I can tell you that these ratios differ roughly by the pressure. So there's about a factor of 15 difference in the value of the stretch rate that the flame sees. So you say, okay, well now how could I learn about mechanisms for blow-off at a high pressure condition from an experiment at 1 bar? What might I do? So I think first of all you could say was, well, presumably, if I were at identical, if all my other conditions were identical, if I was at the same fuel-air ratio, same velocity, and I was looking at 2 flames, one with high pressure and low pressure, I would expect the 1 bar flame to blow off a whole lot easier than the 15 bar. All right? But suppose that you want to emulate blow-off for the 15 bar configuration. How might you scale that? How many of you have wrestled with this problem? Well, what can you do? Well, one thing is you could run the 15 bar case at maybe a lot lower fuel-air ratio. That might be one thing that you could do. You could try to drop its cap extinction value. The problem with that is that you start changing other things, right? As you change fuel-air ratio, you're changing significantly the gas expansion ratio across the flame, the ratio of burned to unburned gas density, which has very, very significant impacts on what the flow fields look like and the fluid mechanics and the hydrodynamic instabilities that are disturbing the flame. Another thing that you could do is you could increase the flow velocity. You could you'd say, no, I want my flame to blow off at the same fuel-air ratio at 15 bar as at 1 bar. So the way I'm going to do that is I'm going to run it at a totally different flow velocity. So if your real engine is running at, let's say, 150 meters per second, and you happen to think that there's a 15-to-1 scaling effect, that maybe you want to run a flow velocity of 10 meters per second in your lab, then you have to start asking yourself, okay, am what I doing in my lab by understanding the phenomenology of blow off when the flow velocity is 10, how much is that going to compare with what's happening when the flow velocity is 150? It's not obvious that there could be significantly different flow features with those different flow velocities. So understanding limit phenomenon, this is an example of a limit phenomenon, extinction. Scaling is a hard problem. I mean, combustion, one of the big challenges with combustion, and one of the reasons that so many of us make a living off of combustion is just because it's hard to scale, right? It's really, really hard to scale. It's really hard to emulate in simplified lab environments without really deeply understanding what's happening and understanding what the limitations are on a given test or a given experiment, just because, in this case, pressure effects are difficult to scale. But when we talk about combustion instabilities later on, combustion instabilities are notoriously difficult to scale. Here's some other data. Again, I'm just going to show you, this is from a paper from Combustion and Flame, Greg Jackson. It just shows these are measured extinction stretch rates for some different hydrogen, methane, air flames. So each line is for a given fuel. So for example, this line is methane, pure methane. This slide is 17% hydrogen. This slide is 31% hydrogen. So you can see that as you go up in equivalence ratio, the extinction stretch rate increases. That makes sense. Flames can withstand higher values of stretch as you're at higher equivalence ratios, presumably because higher temperatures are faster reaction rates. And so therefore, if you think about a normalized stretch rate, this is a dimensional stretch rate. If you were to normalize it by a chemical time scale, as you're going up in equivalence ratio, the chemical time scales are also getting faster. And so you can withstand a higher stretch rate. What's also interesting is even at a given equivalence ratio, hydrogen in particular is very, very, hydrogen flames are very, very resistant to stretch. So you can see at the same fuel-air ratio that by going from methane to 30% hydrogen, you increase the extinction stretch rate by about 50%. And again, this goes to observations that, when you add hydrogen to fuels, it makes the fuels a whole lot harder to blow off. And this is telling you why. Also, hydrogen flames are really, really, it's really, really hard to not have hydrogen flames flash back. Because if you think about what's happening, what is flashback? Flashback, boundary layer flashback at least, is where flames are propagating in boundary layers, which are very thin, very high shear regions. The flame is very strongly stretched in those boundary layers. And so one of the things that causes flames to not propagate up boundary layers is because they're next to walls, and so there's strong heat losses. So the flames are highly non-adiabatic. But they're not only are they highly non-adiabatic, they are also very strongly stretched. And so they can be quenched in those boundary layers, whereas hydrogen flames can withstand significantly higher stretch rates. And so this is another reason why hydrogen flames are so prone to flashback. Here's another plot. This is another set of data just showing you preheat effects. So we talked about how one of the characteristics of high activation energy chemistry is that the phenomenon of extinction is a high activation energy phenomenon, right? If you had zero activation energy, if you had no thermal sensitivity, burning rates would just monotonically and smoothly go to zero. So there's two ways that you can vary activation or dimensionless activation energies. If you remember, for example, Professor Seshadri, I believe he called it a Zeldovich number. The Zeldovich number was a ratio of activation energy over a temperature. So either the dimensional activation energy of the reaction, if that drops, or equivalently, if you increase temperatures, that EA over RT ratio goes down. And so an experiment that people will oftentimes do, in fact, this experiment right here, what I'm going to do is I'm going to show you some calculations where rather than running it symmetric, if we run an asymmetric stagnation flame, where I have premixed reactants stagnating against products. And what I'm going to do is I'm going to show you some calculations for different product temperatures. So at 1350 K, in fact, I'm not showing you the whole curve. Let me just show you what that looks like. So this is strain rate. I don't remember the equivalence ratio. I'm just going to speculate on what's happening then. So this is a consumption speed defined with respect to the unburned density. So that's what you're seeing there at 1350 K. You're just seeing the tail end of it. All right. Actually, no, I'm broadening it from 0 to 200. Never mind. Okay, it's all there. Excuse me. This would be a mixture with a positive Markstein length. So in other words, it's going like this. That's what you're seeing at 1350 K. At 1400 K, and remember that temperature is that product temperature. Notice how you get a behavior, and by the way, if you were to calculate the whole thing, it would look like this. That would be the other solution. The rest of it. Now at 1400 K, you can see what it does is it goes like that, and at 1450 K, it goes like that. Well, that's kind of interesting because what it shows you is there's 1400 K is kind of this magic number that differentiates one kind of behavior, S-curve behavior, and essentially what's happening is you have the S-curve. The S-curve is getting stretched out as you're increasing the temperature, and you're losing the S. And so now you really don't even get extinction anymore with this higher temperature, right? Rather, what's happening is you're increasingly stretching the flame. That what's happening is well, the consumption speed's going down, and that's just a way of telling you that the amount of fuel getting burned is dropping. That if you were to calculate the amount of fuel that's not burned, well, a value of 0 would be 100% of the fuel not burned, and it's basically just smoothly monotonically dropping where you're going from burning, in essence, 100% of the fuel, to 50% of the fuel, to 25% of the fuel, and that's what happens when you go to these very high preheating levels. What's interesting is if you look at the displacement speed, this is consumption speed, always positive. The displacement speed, you can see how it starts to swing negative at those low. These really low consumption speed values. You can see that there, and you can see that there. All right, one last point I want to make about highly stretched flames is that the strong stretch the strong stretch measures of flames, these are not these are not quantities which are intrinsic to the mixture, but they're a function of the system in which they're measuring it. All right. So in other words, as an example, kappa extinction. Well, let me back up. Laminar unstretched flame speed. That has a fairly rigorously defined definition, which is a property of the mixture, right? And a good experiment, you try to measure it so that it's independent of the experiment that it's in, right? That's the laminar flame speed. The extinction stretch rate is not only, it's not just a number for a given mixture. It's a function of how you're stretching the flame. And just to illustrate that, what I have here are three different geometries. Okay, this is the opposed jet. So this is that stagnation flame where we have two premixed jets stagnating against each other. And you can get, that is the opposed flow twin flame calculation, the black line here. So this is the consumption speed normalized by its unstretched value. This is the dimensionless stretch rate. You get this black line, right? And you can see that the consumption speed goes up by about a factor of 5 for this particular flame. It's a hydrogen air flame, which is why it's so sensitive. This is a flat flame. It has no curvature. So all the stretch is coming from that tangential gradient term. There's no curvature. Another way to strain a flame is to have an expanding cylindrical or spherical flame. So this would be the time-varying curvature term in the stretch. If you remember, it was that VF dot N over the radius of curvature of the flame. So imagine if I have some reactants and I ignite them, and then I watch the flame propagate. All right. If the flame was stationary and the streamlines were normal to the flame, remember we said that's an unstretched flame, but because the flame's moving, that's a stretched flame. And so as the flame propagates, initially the radius of curvature is small, and so the stretch rate is high. And then as the flame propagates out, the stretch rate drops. But we can calculate the local consumption speed at every instant of time as that flame is propagating outward. And it can be a cylinder or it could be a sphere. And so you can also do this numerically. So you have this, here I'm showing you this is a cylinder. And what we do to initialize these calculations in order to simulate ignition for what I'm showing you here is that we replace some radius of, so imagine that I have this bath of reactants, but I replace some radius of it with products at the adiabatic flame temperature at some initial radius, which I've called R initial. And then I let the calculation go. And there's some ignition transient as it goes because this is an unsteady calculation. And the flame propagates outward, and as time evolves, stretch rate is dropping. So that's these calculations here. This one, you can see the initial radius is half of a flame thickness, which is the blue curve. The cyan is where it's 0.75, the green is where it's the flame thickness, the purple is where it's 1.5, and the red is where it's 2. And so, and then in essence what's happening is that time equals 0 is the beginning of the hook, and this thing kind of goes like this, and it swings around, and as the radius gets bigger and bigger, it goes like that. Or time equals 0 is right here, and then it goes like that. So you can see you get these, for these bigger ignition kernels, you get these kind of weird results. This is the ignition transient. That's what you're looking at here. So you really, lots of times when we show these plots, we will oftentimes just notch these out because these are transient effects. But main thing you can see is, notice this blue curve and the black curve is different, right? And it just shows you that the sensitivity of this flame to stretch between these two configurations is different. Now let me just back up for a minute here to something that I showed you earlier, where I said asymptotic analysis shows that in the linear limit of weak stretch, the effect of various types of stretch on flame characteristics are the same. So in other words, whether you stretch, if you think about these different definitions, I introduced kappa S, I introduced kappa curvature, or over here I introduced kappa A, and here I introduced kappa B. You might say, well, you know, how's the flame going to respond to kappa A versus how would it respond to an equivalent amount of stretching for kappa B? And the answer is, for weak stretch, doesn't matter. It's just the overall stretch rate that the flame is sensitive to. For strongly stretched flames, it turns out that if you stretch a flame through this term versus if you stretch it through that term, you get a different answer. All right? And there's a couple reasons for that. One is just that the sensitivity of that for strongly curved flames, that the curvature term shows up in the diffusion operator versus this tangential convection term shows up in the convection operator, and they just start to act differently when you really start to radically disrupt the structure of the flame. Or if the effect of the stretch is through sort of steady stretching, this term versus unsteadiness. So the bottom line is you get a different answer. In addition, I've shown one other type of calculation. This is what's called a tubular flame. And in a tubular flame, what you do is it's like a stagnation flame, but it also introduces the effect of curvature on a stagnation flame. So imagine I have two porous surfaces. This red line would be a porous surface. And what I'm doing is I'm running reactants through it, and the reactants are coming out of the porous surface outward. And then I also have this reactants coming in this way. And so reactants are going out, they're coming in, and they're stagnating here. And then the hot combustion products basically flow out both directions. And actually, people have built these things experimentally. There's a group in Japan that has developed these, as well as Bob Pitts has built these things. And by changing the diameter, if you take this thing out completely, what you'll end up with is a cylindrical flame that sits somewhere, and the combustion products go out through the inside of the flame. But if you put this thing in, as you change the radius of this thing, of this inner tube, you can actually change the radius of curvature of the flame. So this is a steady configuration where you're having both. You have both. The flame is both curved as well as there are tangential gradients. And so I'm showing you a calculation for the tubular flame. That's this yellow. And you can run different tubular flame calculations. Bottom line is all these plots are different. And so there is no that the sensitivity of flames to high stretch values is intrinsically a function of how you're stretching it. All right? Does anyone have any questions? Yes?
All those plot you showed for the stretch rate versus velocity, they are calculated.
These are all calculations.
How do you decide the extinction limit? Is it just the part where the curve comes back, or how is it validated with the experiment or something?
So yeah, that's a great question. Is what's the validity? Well, I think you're asking what are the validity of the mechanisms out there. I think some mechanisms are validated, some of them aren't. So I don't know the specific answer for hydrogen air, how well validated those calculations are for high stretch values. But it's a good thing to check on and be aware of. Okay, we have 15 minutes, and so I just want to quickly talk a little bit about flame stabilization and shear layers now, and some of the application of these ideas to flame stabilization and shear layers. And in particular, what I want to talk about is what does the stretch rate look like when you have a flame that's sitting in a shear layer? And so there's a couple, and so what I'm going to be thinking about is here's my model configuration. Here I have a flame, and it's spreading away from a wall. And basically, the flame is going to get very, very close to the wall because the velocity is nearly zero because you have this boundary layer. And you have very, very strong hydrodynamic straining. So I wrote that here. I have that term written up. Let me just back it up so you can see which term I'm writing here. Here's our definition of stretch. You have this flow. This is the stretch term due to flow non-uniformities. This is the stretch of a curved flame in a uniform flow. What I want to do is I want to specifically take a look at this term specifically. All right, and so what I've done here in your notes is I've written it up in tensor form. So it's delta ij, this is just the Kronecker delta, minus ni nj times dui by dxj. And again, for reference, the fluid strain rate is 1/2 dui by dxj plus duj by dxi. So remember, I called this Sij before. And you can see there's some similarities here. You can see that, you know, there's this term, but you can see also that the fluid mechanic straining rate is not the same as the flame stretching rate, which again is why I like to use the word stretch when I'm talking about a flame and strain when I'm talking about the flow. And then these n's, ni and j, denotes the normal, the flame normal. So if I assume that the flow upstream of the flame is incompressible, which basically just lets me say duz by dz plus dux by dx is 0, and it's 2D, then I can take this expression and I can write it in this way. So I can take this expression, I can evaluate these velocity derivatives, and I can write it this way. And what I've done is I basically bracketed two contributions to flame stretch. One is flame stretch associated with normal straining. All right. So normal straining is taking a fluid mechanic, a fluid volume, you squish it, an incompressible fluid volume. If you squish it and simultaneously pull it so that its volume stays constant, that's normal straining. This term right here, which has the diagonal elements, is the shear strain. That's taking a fluid element and shearing it. And you can see how both of these are contributing to flame stretch. Well, let's just draw a picture now of how that's working. Why are flames stretched when they're in a shear layer? Let's talk about that first. So let's talk about what makes this term non-zero. Well, easiest way is just to draw a picture. So here's my flame. Here's my velocity vectors, and I'm going to assume that I'm zooming in at the boundary layer. So the velocity is going to 0 near the wall and then increasing as I move away from the wall. So this is what my velocity field looks like. All right, and I've drawn just a very simple velocity field. In reality, it'll be curved and bent and things like that. But if I take this velocity field now and I decompose it into its contributions normal to the flame and tangential to the flame, that's what I've done here. Okay? And can you see now why this flame is stretched? The tangential component is changing in the tangential direction, right? So that's the tangential direction. Tangential velocity is not constant. Tangential velocity alone doesn't stretch a flame, right? If I can have a tangential flow. If this was constant at every point, I wouldn't have the stretch. There wouldn't be any stretching. But it's the fact that the tangential velocity is changing. So what direction would this be, positively or negatively stretched? Positive, right? You can see it's stretching this thing out. So this is what's happening. And so now what would I have to do to what flame shape would give me 0 stretch? What would the flame look like? Yeah, if the flame was completely flat, not sure how I would do that, but if I could somehow cook up some flame speed profile, if the flame is completely flat, there would be no tangential component. That's not very practical. Was there another way? If the flame was perfectly vertical, right? If the flame is perfectly vertical, then there would be again no tangential component. Excuse me, there would be no gradient in the tangential velocity along the flame. You'd have a very strong tangential component. So if it was flat, there would be no tangential component. If it was vertical, the way I've drawn it here, you don't have that gradient in tangential velocity. So it's the angle of the flame with respect to that shear layer which is driving this. And what you can also see is that as this flame becomes more and more steeply angled, that for a given gradient in velocity, the flame stretch rate is going to be dropping, right? In fact, let's just show you what that looks like. If you actually work out the math, if the flame has an angle of theta, this is what I'm showing you here. And so I'm just going to do some analysis here, assuming a very high-speed flow where the velocity is much higher than the flame speed, so the flame has a pretty steep angle. So if theta is small, theta being measured in radians, you can show that the shear term, kappa shear, is equal to theta times duz by dx. So duz is the velocity in the z direction. Here's my coordinate system, z, x. So the velocity in the z direction, how it varies in the x coordinate. So it's the shearing velocity, right? And so what you can see here is this is basically the strain rate, the fluid volume strain rate. This right here on the left is the flame stretch rate. And so what does this equation say? How is flame stretch and fluid strain related? By theta, right? Flame stretch, fluid strain. For this problem, they're related by the flame angle, theta. And so what this means is life's hard because, for these really, really, oftentimes many of you may do experiments where you're running in really high velocity flows and the flame looks almost like it's parallel to the flow. So if you say, assume the flame is parallel to the flow, that would give you a flame with zero stretch. So it's that small angle of the flame with respect to the flow that's giving you the non-zero stretch, which at some point the flame will cause the flame to extinguish and to blow off. But it also means that the difference between a flame angle of theta of 0.1 versus a flame angle of 1 degree, which from an experimental point of view, you're probably going to have a really hard time differentiating an angle of 0.1 and 1 degree, right? Or as measured with respect to the other coordinate, 89 versus 89.9, that those can give you a 10x difference in stretch rate. So we've actually done this where we've gone in and tried to measure flame stretch rates, which is what I'm showing you here. And just look at these error bars. I mean, the error bars are just enormous, right? So, here this is a normalized stretch rate. I'm normalizing it by a reference quantity, but you can see the error bars are, on the order of 100 or 150% of the mean values. And that's why, it's because theta, this flame angle is quite small. Now, one other source of flame stretch I've talked about, so we just talked about the shear strain contribution. The other source of flame stretch is that normal strain contribution. And I don't want to discount this because oftentimes when we see flames sitting in shear layers, there's enormous fluid mechanics straining going on. So for example, if you have a 50 meter per second flow and it's going to from 50 meters per second to 0 over a distance of a few millimeters, which would be a pretty typical number, those are strain rates of, well, if it was 1 millimeter, 50 meters per second divided by 1 millimeter is 50,000 inverse seconds. So the fluid mechanics straining could be 50,000 inverse seconds, whereas the flame stretch is 50,000 times whatever that flame angle is. So if that flame angle is 1 degree, it would be substantially lower than that. So just because you have these enormous strains, and the flame, just because you have these enormous shearing strain rates, that doesn't necessarily mean that the flame is highly strained because it's getting multiplied by that flame angle. So the problem is you're multiplying a big number times a small number, and you're worried about that product. Now the other way that you can get flame stretch is through that normal term. So if we go back to this equation, this term right here. So the way this works is shown here. Here, again, just to keep life simple, I've neglected the boundary layer, but if I have a velocity that's decelerating in bulk, so if the velocity vectors go like this, to this, to this, to this, and this is oftentimes the case in combustors because you're oftentimes going from a small diameter pipe, let's say a nozzle, to a big diameter combustor. And you want a small diameter nozzle in order to avoid flashback, right? You have a very high velocity, and so the flow in bulk is decelerating pretty rapidly right in the region where the flame is stabilizing. So if you were to, again, take this velocity and you were to decompose them into a contribution that's normal and tangential, so here I have it, here I have it, here I have it, this flame is stretched, right? And is the stretch positive or negative? Yeah, I guess I put it right there. It's negatively stretched in this case, right? Because the tangential velocity component, it's getting negatively stretched. Now, what's happening here is if you actually work through the math, here I showed you that the shear term goes like this. This is, again, this is another component of the fluid mechanics strain rate tensor, right? This is the normal strain. The shear strain is getting multiplied by the flame angle. The normal strain is approximately equal. Now, in general, which quantity do you think is going to be bigger in a combustion flow? That term or that term? The shear strain is going to be a whole, the du/z by dx is going to be a whole lot more than du/z by dz. But this one is just sitting by itself. This one's getting multiplied by theta. So an interesting question is, well, what's the dominant source of flame stretch in a real flame? This could be very highly configuration dependent. We've done some measurements in our lab. We actually found that this term was bigger because it was not getting multiplied by the small theta. Although this term was a factor of 10 bigger than that, it was getting multiplied by the smaller theta. So this brings me back to this point around blow-off, is although we know flames blowing off, that it's oftentimes very intricately related to extinction, scaling, actually predicting and scaling what the stretch rate that the flame is seeing is really tricky, because you're really looking at the superposition of two terms, one term being a lot smaller than the other, but the term that's big being multiplied by another small quantity. Small uncertainties can really blow up. All right. I think that we will stop there. Does anyone have any questions? Yes, sir.
Why is it decreasing at the end of the strain rate? First it is increasing towards the wall, and suddenly at the end it is decreasing.
You're saying here? Yeah. Okay, so this is data from a swirling flow where we actually went in and measured the stretch rate. What's happening is that, so what I'm showing you here is the overall stretch rate is shown here. And then I'm showing you these different contributing terms. So let's see, this would be a strain, the x's is a shear strain term. That's this term right here. It's positive, as we talked about, it's positive. The diamonds here is that deceleration term, as we talked about, it's negative. The other two terms are pretty small, and I neglected them in the discussion here. What you're looking at is the sum of a big positive term and a big negative term to give you the overall stretch. And remember, whenever you're adding two terms of opposite sign, errors, small changes can have a big effect, right? If I'm adding 5,000 plus negative 4,998 versus 5,000 plus negative 5,002, I get one's a positive number, the other's a negative number. So the overall stretch rate is pretty sensitive. You can see that near the attachment point, the overall stretch rate is actually negative because that deceleration term wins, and as you move downstream, the stretch rate becomes positive. Any other questions? Yes?
Very different in turbulent combustion. The turbulent flow has turbulent energy cascade.
Yeah, I'm listening. Yeah.
You observe that in flame curvature. Does that also have a similar cascade? Or is it smoothing the scales observed in terms?
So you're asking me is what is the wave number spectrum of flame wrinkling?
Yeah.
Yeah. So all right. So that's a very interesting question because if you think about a turbulent length scale with length scale Li, it's going to have an associated velocity. I'll call it UI. UI is not a scalar. It's the velocity. I'll call it U prime. Boy, that doesn't look good. The velocity fluctuation associated with the ith length scale, right? So if we have Here's your turbulent cascade. Here's the wave number spectrum. So what causes flame wrinkling? Flame wrinkling happens when U prime on SL is greater than 1, right? This is, if U prime on SL is less than 1, the flame can propagate faster than the velocity disturbance that's wrinkling it, and the flame is very weakly wrinkled. When U prime and SL becomes much greater than 1, that doesn't happen. So what happens is that because U prime, the velocity fluctuations associated with the larger scales are bigger, that you can imagine now that you could have, if you want to know the degree of wrinkling associated with a given length scale, imagine looking at UI on SL. And it's going to transition from, for a highly turbulent flame, for big length scales, it's going to transition from being much greater than 1 to being much less than 1. So there's actually a quantity out there called the Gibson length scale, which is the length scale where UI is equal to SL. And this is, in essence, the smallest length scale on the flame. So the flame has because of flame propagation normal to itself, that has a filtering property that filters out the smallest length scale disturbances. Any other questions? All right, have a good evening, and I will see you tomorrow.